Up to this point, we've exploited several relationships between cell potentials and free energy. I want to take that to its limit and talk about ionic free energies of formation in this video. So recall our convention that the standard hydrogen electrode is going to be defined to have a standard reduction potential of 0 volts. And so insofar as it's also true that a standard potential is equal to minus the standard state free energy of reaction divided by number of electrons and the Faraday constant, it must be the case that the standard state free energy of reaction for this reaction is defined to be 0. Of course, it's also true that the standard state free energy of reaction is the standard state free energy of formation of an aqueous proton plus the standard state free energy of formation of an electron, those are the two products, minus the standard state free energy of formation of the reactant, H2. But each of those two things at the right-hand side of that equation, the electrons and the hydrogen gas, are pure elements. I guess I have elements in quotes because an electron isn't really an element, but let's adopt a convention that says we treat it the same way when it comes to free energy of formation. And so if this is 0 and this is 0, and by our electrochemical convention this is 0, then we are left with the only thing left in the equation, the free energy of formation of an aqueous proton at unit activity, so let's remember that, so a 1 molar aqueous proton, is defined to be 0. And that's just a consequence of the convention we adopted for the standard hydrogen electrode. And once we've got a single ion set, the proton that is, again, all the rest can be determined from cell voltages that relate back to that ion. We've got a way to determine free energies of formation for all the other species as well. And so just as an example to do that, here is a fairly straightforward reaction. We're going to mix hydrogen and chlorine gases. This is one of those don't try that at home experiments. Spark them, if you like, in water, but we're actually interested in doing controlled electrochemistry. So we will control the reaction of these species to make aqueous protons and aqueous chloride anions. We know the standard potential for this is going to be the sum of the standard hydrogen electrode and reducing chlorine, and so we've got 1.361 volts. It's also the case that minus NF times that 1.361 volts is the free energy of reaction, which is the free energy of the products minus the free energy of formation of the products minus the free energy of formation of the reactants. Once more, pure element 0, by convention now 0, and that allows us to solve trivially for the free energy of formation of chloride anion in solution at unit activity minus 131.2 kilojoules per mole. We could take advantage of temperature dependence, which we looked at in the last video, and turn these free energies of formation into enthalpies of formation, heats of formation if you like, as well as entropies. And so we are able, by the standard hydrogen electrode convention, to assign to any ion in solution a free energy of formation, a heat of formation, an entropy of formation, and that gives us the full power to take advantage of things like Hess's law and all the materials we used in Module 12 in order to understand how free energies change as you have reactants and products in equilibrium with one another or out of equilibrium. And so that leads to huge tables. I always like to talk about these big thermodynamic tables. So here's a big table. Summary of the apparent standard partial molal Gibbs free energies of formation of aqueous species, right? So here's where we've managed to harness electrochemistry to take us into aqueous solution. For minerals, gases at pressures of 1 to 5,000 bars, temperatures of 25 to 1,000 degrees Celsius, You see all these different authors on this particular piece of work, which spans hundreds of pages in the Journal of Physical Chemistry Reference Data. And it's interesting to look at what some of their affiliations are. Geology and geophysics, because geochemistry is terrifically important, the movement of ions through groundwater, for example. Space sciences, because you want to know what's going on in your interstellar nebulae, and thermodynamics gives you a handle on that. National laboratories and places that are interested in standards. And then the inside baseball that actual practicing chemists will appreciate is this manuscript received March 1st, 1993. Some referees must have looked at it for a long time, or else they asked for a whole lot of things because the poor authors spent more than a year revising it, sent in the revision on October 27th, 1994, and probably it had to be reviewed one last time and then finally got published in 1995. So that's pretty unusual that you submit something and it doesn't come out for 2 years. But that's just because this was a huge body of work, and you know, if one's going to tabulate data that many, many people are going to use, you want to be sure that is bulletproof data. You don't want to be responsible for someone building a large chemical engineering plant that leaves a big smoking hole in the ground because you moved a decimal place one to the left or right in a critical component of what was happening in that plant. Doesn't happen very often, but anyway, that would be the concern and why we need good standards. All right, let us continue to travel with the train and reach a very practical application of electrochemistry that I want to talk about, and the thermodynamics behind it, and that is batteries and fuel cells. That's what's next.